6.5 is where you're at. We're going to take a look at this topic called logistic equations. You've seen exponential equations before in chapter, I guess, 5? Yeah. But now I want to show you that most of the time exponential growth assumes unlimited growth, and that's pretty unrealistic, right? Most populations, they don't grow forever. If that's the case, our whole world would be covered in spiders or whatever else that you don't like, and life wouldn't be so great. But more typically, the growth rate actually decreases as the population grows, and there is something called a maximum population, called the carrying capacity, and we use the letter M to represent that. So this model, when you have this maximum population, is modeled by the logistic differential equation, and the logistic one is a little bit different than the exponential one. Remember, the exponential was just dy dt equals to ky, right? It's constant multiplied by the y value. Here now we've got the k times p. Of course, p is their population, but now there's a limiting factor of this m minus p. Okay? Now, the solution to this differential equation is really just this. Okay, so you go from there to there. Okay, but unlike the exponential growth equation, c is actually not the initial amount. Okay, so be careful about that. Now, if you don't memorize these two equations that I put in the box, not a problem. You can actually find this yourself by using the methods of, I will remind you, last day I told you needed to use partial fractions. So in this example, I will actually show that to you here. So here's our first and only example for lesson 6.5. There's a national park, and it's capable of supporting no more than 100 grizzly bears, because 101, well, that's just too many, and they'll start to fight, and they'll kill each other, and then they'll be back to 100. So we model the equation with a logistic differential equation. The k value in this case is 0.001. So if I ask you to quickly just write the differential equation, you're looking up here now and saying, okay, let me use this differential equation, dp dt, and the k value here is 0.001 times p, and p is your variable. And then because we know that there's no more than 100 grizzly bears, the m value is 100. So there is my logistic differential equation. Now, part B says the slope field for this differential equation is shown to the right. And if I ask you to look at the slope field, can you figure out where the horizontal asymptote is going to be? Can you kind of see how the horizontal asymptote probably looks like it's right here at 100? Which I think makes sense, because I'm telling you there's no more than 100, so your graph cannot be larger than 100. But what happens if the starting point is above this asymptote? So let's not worry about the context of this question, just look at the actual slope field. If the starting point was above, so I'm just going to use my green highlighter, say, I don't know, somewhere up here, what do you think happens? Well, it looks like the population then decreases towards the asymptote. Decreases, I'll say the population decreases towards the asymptote. And what happens if the starting point is below this asymptote? So something down here. Well, if you look, it seems to increase but then flatten out towards the asymptote as well. So in this case, the population increases towards the asymptote. Now, in our case, we're talking about a park, and the park actually begins only with 10 bears. So if it only begins with 10 bears, the question here is, can you sketch a graph of the actual population function on this slope field? So if I were to take 10 as the initial population, that's probably right about here, and I follow this slope field, I'm thinking everything has to be parallel, parallel, parallel. I'm thinking the graph looks something like this. Okay? And your logistic graph or the function of p looks like that. Okay. So C graph. And once again, you should see that this now gets closer and closer to the line of 100. Okay. Now turn the page, and this is the part where I asked you to know last day's material really well. Because now I'm going to ask you to solve that differential equation. So once again, that differential equation from the previous page was dB dt equals to, I'll call it 0.001p bracket 100 minus p. And to do this, I'm going to ask you to separate the variables. So let's put the p's on the left side and put the dt on the right side. Okay. And once again, separation of variables means I should be integrating both sides. And then you should be thinking to yourself, this seems to be a partial fraction. Yes, yes, yes. Can you rewrite this as a over the first term, b over the next one, and that's supposed to be equal to this? Remember this stuff from last day? So we equate the numerators. I'll let p equal to 100, and that means that the a value is 0, and we get b equals to 1 over 100. And of course, if I let p equals to 0, then I believe we get a equals to 0b, and so I think a is also equal to 1 over 100. How lovely. And so, if I asked you to really integrate this now, let's separate this into a partial fraction. There's my a over p. Here's my b over p. And we're going to integrate this with respect to dp. While the other side here, I still have the integral of 0.001 dt. Okay, so I just went from this step here down to this one here. Okay. And now I hope you're ready to anti-differentiate. So, doing the antiderivative, I hope you can see I can take out a 1 over 100. And I'm going to try to skip a few steps. 1 over p, that's just natural log of p. We don't have a minus here because of the minus in the p. So that's natural log of 100 minus p. I'm going to put an absolute value around that. The antiderivative over here is 0.001 times t, and then of course plus c. Okay. If you want to remove that 1 over 100, I can multiply both sides by 100. Okay. And then I'll get the following up here. I'll get the natural log of p minus natural log of 100 minus p equals to, I guess that's 0.1t, and I'll call this some other constant. Let's call it c1. And so far so good, I hope. And then I'm also going to do one little trick. I'm going to take out a negative from the left-hand side, and you'll see why in a second. If I take out a negative, this becomes now negative ln p plus ln of 100 minus p. And I'm going to do that because I want to actually take this negative sign and now stick it on the right-hand side. So when I do that, notice I'll have the following. Negative ln p plus ln 100 minus p equals to negative 0.1t. I guess this is another constant. Let's just call it c2. Notice why is this helpful? Because now I can now rewrite the ln as one term as just 100 minus p over p. And you're thinking, who cares? Well, here's why you should care. Remember, our goal is to try to solve for p here. So to get rid of the ln, I'm going to now e both sides. Whee, whee. And now you're just left with 100 minus p over p equals e to the power of negative 0.1 t. And then this is the same thing as multiplying by e to the power of c2. Okay. I can rewrite this lovely part as just another constant, and I can try to also simplify this part over here to 100 over p minus 1. So I'll just write this like that. Let's call it c3. And why is this kind of nice? Because I think you're getting closer and closer to solving for p. Yes, a lot of work. 100 over p equals to 1 plus e to the negative 0.1 t times c3, or some sort of constant. And if I want to solve for p, I'm going to flip this around because I want p in the numerator. So how about p over 100 now equals to 1 over 1 plus e to the negative 0.1 t times c3. And finally, you can say p is just equal to 100 over 1 plus, and let me call this c3. I'll just call it c3, whatever. c3 e to the negative 0.1 t. Once again, c3 is just a constant. And there you have it. There's your population equation. All that work, yes. But wait, it says we have initial condition, so let's plug that in too. Let's plug in now the initial condition. What was the initial condition again? Yeah, you forgot. 10 bears at the beginning of life, or beginning of population. So therefore, if I put p equals to 10, and I keep t as 0, you should be now able to solve for c3. So that, I believe, is just 100 over 1 plus c3. Divide both sides by 10 like this, so 10 equals to 1 plus c3. So c3 equals to 9. So all this work for the particular equation of p equals to 100 all over 1 plus 9 e to the negative 0.1 times t. Woo! If you missed part of this, go back and check the work. I've tried to show you as many steps as I could. But there you have it. This is the actual population equation for this initial condition. Now, if you're thinking, do I need to do all these steps every single time? Yeah, I guess so. Unless you memorize the general form of the logistic equation. So remember, I boxed this also on the previous page. So you could just go directly to here by using this formula as well. So if this is the case, if you didn't want to do all that work in part D, you'd say to yourself P equals to M, which is the carrying capacity, that's 100. 1 plus, and you're still missing the C, e to the power of negative k. We know the k value was 0.001. M is 100, so I'll multiply that by 100 times t. Okay. And of course this simplifies to p equals to 100, 1 plus c e to the negative 0.1 t, which is exactly the same as what I had over there in part D. Of course, you need to then find the general solution, the initial, you need to find the specific solution with that initial condition of 10. So I'll plug this in, and you get the same business as before. I don't need to do this again, I hope, but you'll get the same thing, c equals to 9. So therefore, by knowing this equation and plugging it in, you'll also get the same answer as part D. Part D, however, is the actual mathematical process of actually getting that equation. All right? Okay, 2 more questions, and I'm going to let you try some questions on your own. When will the bear population reach 50? So when means find time, and of course the population is 50. That just means use your equation from above, so 50 equals to 100. 1 plus 9 e to the negative 0.1 t, and you're going to solve that. If you're going to solve that and you need my help, I'd say 1 plus 9 e to the negative 0.1 t. That equals to just 100 divided by 50, or 2. Right, just rearranging them around. Subtract 1 on both sides. Divide 9 on both sides. Law on both sides. And then you should be able to solve for t. And I believe the answer here, if you don't want to do it yourself, is about 21.972 years. So after about 22 years, you'll get 50 bears. H is the most interesting question of all. When, so let's gain time, is the bear population growing the fastest? So I'm asking you the bear population growing, that's the rate, and when is it growing the fastest? When is the rate a maximum? The maximum of a rate. So I want you to find the maximum of dp dt. I hope you remember how to find the maximum. Way back in chapter 2 or 3 we did this. Yes, you would actually take the derivative of that. So dp squared dt squared, and then you want to make the derivative equal to 0. So I guess we should actually figure out what dp dt is first. That from our equation is 0.001 p times 100 minus p. Let's distribute that. And if we distribute, I think we get 0.1 p minus 0.001 p squared. So that's my derivative, and I'm asking you to find the max. You're going to take the derivative of that derivative and set it equal to 0. Basic power rule here up. And if I make this equal to 0 and solve for p, what do you get? I think it's 50. And once again, you should double check. When the population is 50, do your number line, remember this, to prove that it's a maximum. I know that this is positive, this is negative, so 50 definitely is a max. So when is the bear population going the fastest? It's going the fastest when the population is equal to 50, and it just so happened that the population equals to 50 when the time is equal to 21.972 years. And if you're curious how I got that so fast, that just was the answer from part G. Alright, this was hard. If you understand this, bravo. There's one more topic left in Unit 6, or Unit 6, and then you're done. So, go and try some questions now, when I assign them in class. See you then.